educational video on the Schumann resonance. In this video, we'll explore what the Schumann resonance is, how it forms, and its relationship with electromagnetic waves and the Earth's atmosphere. Let's begin by understanding the basic concept of the Schumann resonance. The Schumann resonance is a set of extremely low-frequency electromagnetic waves that exist in the Earth's atmosphere. The fundamental Schumann resonance frequency is approximately 7.83 Hz. This means that the electromagnetic energy cycles about 8 times per second. It was first predicted by physicist Winfried Otto Schumann in 1952 and later observed and confirmed experimentally. To understand how the Schumann resonance works, let's look at the Earth ionosphere cavity. The Earth's surface and the ionosphere, which starts at about 80 to 100 kilometers above the Earth, form a natural cavity. When lightning strikes around the world, which happens about 50 times per second globally, they generate electromagnetic waves. These electromagnetic waves propagate around the Earth within this cavity, and when the wavelength matches the circumference of the Earth, resonance occurs. Now, let's look at the mathematical model of the Schumann resonance. The resonance frequencies can be calculated using this formula, where n is the resonance mode, c is the speed of light, and is the Earth's radius. For the fundamental mode, where n equals 1, and using the speed of light as approximately 3 times 10 to the 8 meters per second, and Earth's radius as approximately 6,371 kilometers, we get approximately 7.8 Hz. There are also higher modes of resonance at approximately 14, 20, 26, and 32 Hz. Now, let's look at how we can relate the Schumann resonance to a wave equation model called the UF equation. The UF equation relates frequency, a wave constant, and distance in the following way. UF equals F times K divided by R, where F is the frequency in Hertz, K is a wave constant, and R is the distance in meters. If we apply this to the Schumann resonance, we use F equals 7.83 Hz as the Schumann frequency, K as 6.3 times 10 to the 9, which could represent a property of the medium, and R as 90,000 meters, which is the approximate Earth ionosphere gap. Substituting these values, UF equals 7.83 times 6.3 times 10 to the 9 divided by 90,000, which gives us approximately 548,100. Let's visualize how the UF value changes with different frequencies and distances. First, let's look at how UF varies with frequency when we keep the distance constant at 90,000 meters. As you can see, UF increases linearly with frequency. So as the frequency goes up, the UF value also increases proportionally. Now, let's see how UF varies with distance when we keep the frequency constant at the Schumann frequency of 7.83 Hz. Here, we can see that UF decreases inversely with distance. As the distance increases, the UF value drops rapidly, following an inverse relationship. Now, let's briefly explore the significance and applications of the Schumann resonance. The Schumann resonance has several interesting properties and applications. First, it can be used for monitoring global lightning activity, as increased lightning results in stronger resonance signals. Second, it helps in studying global weather patterns and climate change, as variations in the resonance can correlate with atmospheric conditions. Third, there are ongoing studies about potential biological effects, as the fundamental frequency is close to human brain alpha rhythms. Fourth, it can impact radio communications in the ELF band, which is important for certain types of global communications. To summarize what we've learned about the Schumann resonance, the Schumann resonance is a set of electromagnetic standing waves in the Earth ionosphere cavity. The fundamental frequency is approximately 7.83 Hz, with higher harmonics at approximately 14, 20, 26, and 32 Hz. We can model aspects of the resonance using the UF equation, which relates frequency, medium properties, and distance. The Schumann resonance represents a fascinating example of natural resonance phenomena, showing how the Earth's atmosphere acts as a giant electromagnetic resonator. Thank you for watching this video on the Schumann resonance.